Log on, tune in, find out. Another good idea from Cambridge.
A pleasure to introduce Mike Davies, who is our next speaker. Usually the procedure at LMS invited lectures is that there is one main lecturer and a few one-hour additional lectures that cover aspects of the subject, which the main lecturer is unlikely to cover, and broaden the perspective, etc., etc. Now, Mike was a student in Cambridge, then was a Royal Society Research Fellow at UCL in Cambridge, then passed through many other universities. As he is keen to emphasize, he is not a mathematician, he is an engineer, something about which we are very open-minded.
Hands up who's open-minded.
Hands up who isn't. And now he is at Edinburgh at Faculty of Engineering there, and he'll be talking on compressed sensing in RF. Please.
Okay, thank you. First of all, I'd like to thank the LMS for inviting me to give this talk. I'm going to, as Aria said, I'm an engineer, so I'm going to try and give a math light talk. I hope that doesn't offend too many people here. I should thank all my co-workers who obviously did all the work that I'm going to present, but I'm going to be the one claiming the credit for it. And I should thank my sponsors, which is typically the EU, EPSRC, the STL, and various other people. Okay, so let me give you an outline of what I want to talk about. I'm going to start with my take on compressed sensing, and fortunately this sort of is going to be a very quick reminder of what Emmanuel said in the last 15 minutes of his talk, so hopefully it'll sort of merge well together. I'm then going to talk a bit about practical, what I consider to be practical engineering aspects of CS, what as an engineer I have to worry about when trying to take this beautiful mathematical theory and apply it on some specific applications. I'm going to talk about 3 applications which I should apologize, are tenuously linked via the fact that they all involve RF signals, but other than that they have very little to do with each other, but they sort of emphasize the different engineering issues. And then I'll give some final thoughts. Okay, so let me begin by recapping what Emmanuel said is really the philosophy of compressed sensing. It's this idea that we take lots and lots of samples, typically when we measure things. We then typically transform into to some domain, maybe wavelet, maybe Fourier, and we throw most of them away. And so that's kind of wasteful, and so there's this sort of notion of why can't we sample at the information rate. And I think that the breakthrough was in 2006 when Emmanuel and co-workers and Dave Donahoe published these papers which essentially introduced the concept of compressed sensing and the ideas of compressed sensing, saying that ultimately we can sample at the information rate under certain circumstances to a certain extent. And the ideas, of course, heavily rely on this notion of sparsity. So I'm not going to say too much about defining that. I think Emmanuel's done a lovely job introducing the field this morning. Okay, so this is kind of my small amount of math that I'm going to include on the slide. This is what I see as compressed sensing is composed of 3 important elements. First of all, what we're trying to solve, let's think about that. I don't like to contradict Emmanuel, but I'm sorry, it's not AX equals B, it's phi x equals Y. And just to get our notation straight, K is my sparsity, which is typically less than M for my measurement dimension, which is typically less than N for my signal space. But okay, so what we're trying to solve is an underdetermined linear problem here. We want linear inverse problem. We want to we observe Y, which is phi of x. Phi is dimension reducing, so we're sort of dimensionally challenged, and I want to retrieve x. Now we know that we can't do that, so the first ingredient of compressed sensing is we introduce something that makes the problem well posed. So we introduce this notion of a sort of a set of signals of interest, which are in some way small enough to allow us to actually conceptually try and solve this. So we assume that our signal set is in some way compressible. So that's denoted in this picture by my little sort of star shape. This is like a sort of an LP ball in n dimensions. Then the second ingredient of compressed sensing is we need to engineer our measurements carefully so that we actually preserve the information about that set, at least approximately. And the beautiful thing about compressed sensing is we can do this by using random projections, and then that gives us a representation down in my low-dimensional space that is approximately equivalent to my representation in my high-dimensional space. So that is the key second ingredient. Our measurements that we're making must give us pretty much all the information we want about the signal. And then finally, well, Emmanuel talked about L1 minimization or combinatorial optimization. The key thing is we obviously can't invert this in a linear manner. That wouldn't work. So we're going to have to use some form of nonlinear approximation. And the theory of compressed sensing has introduced some very nice practical algorithms that are both sort of polynomial complexity, but with guaranteed performance. And I think these fall into basically sort of two camps of algorithm. There's the relaxation-based ones that Emmanuel mentioned in terms of L1 minimization, where we convex optimization, and a second set which are essentially greedy in that they're making hard decisions, albeit maybe iterating those hard decisions. And there are so orthogonal matching pursuit, COSAMP, IHT, which stands for iterative hard thresholding. These are all algorithms with guaranteed performance. And right. Okay, so that's all I'm going to say about that. That's my recap of Emmanuel's 1.5 hour lecture. Now I'm going to say, as an engineer, what do I need to worry about? What do I need to ask myself? And there are lots of important questions, but I think there are 3 that are very important. What is the right signal model? It is often considered that this sort of comes along with the signal, and it's immediately obvious to us. If we're doing images, it should be wavelets. If we're doing audio, maybe it should be a short-time Fourier transform. Sometimes the right signal model is obvious, sometimes it isn't. Sometimes the signal may not be sparse at all. I mean, I think this is a really important issue to realize that we may have a particular sensing modality that just confounds us and doesn't allow us to do this. And we'll look at some examples of this. How should I sample? Well, in physics, you're going to be constrained. So it's a nice idea that we can use these Gaussian random matrices, but in practice, my MRI machine doesn't do that, nor does my radar and other things. So I have physical constraints, and there may even be issues about implementing randomness. I may not be able to do it, and I will actually raise the question. It's not clear always the importance of randomness in the measurement process. So I will say a bit about that as we go on. Something that does and should worry all engineers is noise. How do these things behave with noise? As Emmanuel has hinted at, basically these things are robust to noise, but they're robust to a certain extent, and I think how much they're robust is going to be a defining factor on the applications that these things will work in. Maybe we've got something more than sparse. So the sort of the background of compressed sensing started out by assuming that I have a sparse structure. That was my sparse or compressible structure. That was my sort of set of signals of interest. But maybe I have even more information about what I know about the signal. And if that's true, maybe I can do even better. So I sort of see compressed sensing as opening the door to saying we should put Nyquist to one side and start to rethink how we sample. And if there's more structure, the better. Let's see how we can use it. Okay, and a question that I am asked by many practitioners that I still can't really answer is, how many measurements should I take? We have some sort of ideas of how well we can make this, but there are some constants involved that the theory provides us with that means I can't give a nice crisp answer, say like the Nyquist criterion does, which is in some senses disappointing. Okay, and finally, from an engineering point of view, we view these this inverse problem very much from a mathematical sense. I want to recover x, but in practice, I may, as an engineer, have actual different goals. So reconstruction, that may be one of my goals. I may want to reproduce my image from my digital camera because I want to show it to my kids. However, I may want to use that signal to do something else. I may want to do detection. I may want to do some form of statistical estimation. So in that case, one has to, I hope that's not going to keep going on. It isn't, my mobile phone's down there. Anyway, we may want to do some form of ultimate goal that actually means we don't need to fully reconstruct. And I think, again, we need to approach these because this will tell us how to tackle some of these problems. Okay, so I'm going to illustrate these with 3 weakly linked examples, linked on the theme of RF sensing. So the first one is the canonical, what I consider the canonical form of compressed sensing application, MRI. It's a beautiful application where you've got this very sophisticated physics that reduces to sampling your signal in what is actually a relatively simple form. So we have some MRI image, and typically most scanners, so there are, you can do fancy things on very state-of-the-art scanners, but most scanners you either sample your K-space, which is your spatial Fourier transform, either in a Cartesian manner, so you sample in lines, or you sample radially. There are spirals and other things you can do, but I'm not going to really dwell on that. So, and one thing here is that actually it's not the individual samples in K-space that cost you in terms of time, it's the actual lines. You get a line for free. Well, not for free. You get a line per cost. And a line takes roughly 5 to 10 milliseconds, depending on your scanner. So that is what the cost of these things is. How many lines can I afford to take to do my imaging? And what we'd like to do, obviously, is take less lines. So I take less lines. But oh dear, I get aliasing. So this is precisely what we want to avoid. And this is where compressed sensing comes to the rescue. So let me give you, first of all, see my Shep-Logan Phantom comes up beautifully. Bill Gates, wonderful technology. Conceptually, this is the idea of applying compressed sensing to MRI. Here I have my Shep-Logan Phantom. I'm never quite clear what it's meant to pretend to be. Is that meant to be a slice through a brain or anything? But anyway, it's meant to be some sort of archetypal MRI image. It is a word of warning if you actually ever try and do experiments with this. It is truly sparse, up to very, very high signal to noise in the Haar wavelet domain. I mean, we're not talking about something that's compressible. It is pretty much perfectly sparse. So I can take this MRI image I want to scan. I throw away a whole load of my case space samples. So here I'm taking 7 times less lines in case space. And if I were to do a linear reconstruction, I get this. So I actually get some of the structure. It's got the sort of the basic overall structure, but it's lost the detail. If I do compressed sensing, I get perfect reconstruction in this case. And this is true for whether you're doing L1 or a number of the greedy algorithms. Okay, so one thing I should mention, here I'm doing radial sampling. There's no randomness here. And if I were to try and do random sampling, it doesn't really perform much better. So there is this issue, to what extent is randomness a very useful vehicle for defining the theory, for proving things, and to what extent is it actually fundamental? And that's a question I don't have an answer to, so please ask Emmanuel for the rest of the week. Okay, so that's the concept of compressed sensing in MRI. This is the reality. In reality, we're not actually that interested in producing a 2D image, MRI image with compressed sensing. Why is that? Because a 2D slice, well, you can do the maths, it's about 5 milliseconds per line. It takes a second, maybe 2 seconds for high resolution to do a slice. This isn't where the issues are really problematic. The problems occur in more advanced modes of MRI imaging. If you want to do a full 3D scan of the brain, so now maybe you've got 128 slices by 128 by 128. Or if you want to do cardiac imaging, where you're taking an image of the heart and you want to monitor it as a function of time. Or there are things called diffusion imaging, where you're watching how things diffuse around the brain. These things take a lot more measurements, and now your scanning times are going into minutes, not seconds. This is where we're interested. So we have to think about what are the specific problems that we want to tackle, and where are we challenged in terms of the number of samples we can take. Okay, there are some other issues that I'm not going to dwell too much on for the MRI case. You see these images and one might think that the output of an MRI scanner is this intensity image, but actually what you get out is a complex image. So it has phase, and there's a phase, essentially a phase map, a sensitivity map across the image, and that has to be estimated too. And in some cases, so Lustig's early sort of pioneering work on compressed sensing MRI, he would do this by densely sampling the low frequencies and then estimating using that way, and that works in some cases, but it doesn't work in all cases. So there are issues in terms of pulling out the phase. Secondly, we've talked about random sampling, so I could randomly sample in case space, I could randomly choose my lines, but, well, even ignoring the phase aspect where I want to densely sample the low frequencies to try and recover this phase map, because an image, we saw the wavelet transforms of an image typically has dense non-zero coefficients at high resolution, low resolutions, and is sparse at high resolutions, suggests that we don't actually want to do uniform random sampling. So how do we actually sample? I mean, this is a question that the MRI guys I work with are continually asking me, and I'm still desperately coming up with the killer answer for. Even if I have randomness, it may not be controllable. So if you're sampling dynamically for the heart, what you tend to do, so when I first saw these dynamic MRI images, I thought, well, if you can actually acquire that and show me the fully sampled data, where's the problem? Well, the problem is that what they've typically done is sort of anesthetized a mouse, and they've sampled it over many, many heartbeats, and then they've folded it all back, and that's what you see in the data. So this is what's called retrospective gating, where you fold it back onto a single heartbeat, and that introduces uncertainty. When you've got a human patient in the scanner, they've got variable heart rates, and this is going to introduce some uncertainty that you do not control in your sampling. But if we think randomness is good, this can be helpful. Generally, what people do is some form of ad hoc scheme where you have some variable density of sampling across the frequencies, and as I say, the best approach at the moment is very much an open problem. The final point, which I'm going to address more later on, is noise. Like all sensing systems, there is noise. Engineering systems are never noise-free, and a price you pay for undersampling is you amplify noise. And typically, it's 3 dB per octave. I'll show a nice graph of that later. And so one of the limiting factors I think in many compressed sensing applications will be not whether you're recovering the sparse structure, but whether you're fundamentally hitting a noise floor. Okay, so let me give you an example of a non-trivial MRI where we can do some clever tricks and actually get something that it's almost back to Fourier style imaging, so sort of Nyquist style imaging, but it's sort of a halfway house between Nyquist and compressed sensing. So this is what's called velocity flow measurements of the carotid artery. So this is a carotid artery. I apologize if I get any biology wrong. I'm not a biologist. So this is basically taking a scan through the neck. And what we're interested in is looking at the flow in that artery. So we're going to take this whole image, and actually all we're interested in is the flow across that artery as a function of space. And this is how we typically do it at the moment. You have to acquire a bunch of reference frames. So this is a bunch of frames with time and frequency, in a spatial frequency. Remember, we're sampling in k-space, and you acquire that over multiple heartbeats. You then retrospectively gate. That means you fold it back, so you don't quite know where it's going to land in relation to the period of the heartbeat. And you do a second set of measurements where you now encode the RF such that the velocity through the image is encoded by phase. So we now take the difference between these, the phase difference between these images, and this is the artery, and if we blow up as a function of time, we can see little sort of heartbeats going on, and you typically get obviously more flow in the center, and the flow decays down at the end. And as I'm told, this is meant to be very important clinical information to the clinicians. So they like to be able to do this, but we can see now that we're having to do quite a few samples. So if we do a 192 by 192 in space, say I want 24 samples in time across my single heartbeat, and I've got to times it by 2 because I've got to do the reference and a phase encoding. If I wanted to do velocity in 3 dimensions, I would have to do times 4, so I'd have to have a reference and a phase in each direction. So we're starting to having to acquire much more data, and this is something where we are now really would like to speed things up. Okay, so this is in space. It doesn't actually benefit, it's quite sparse actually spatially. It doesn't really benefit that much to use the wavelet transform spatially here. It doesn't gain you that much. So we've typically stuck with just working in the spatial domain, and in the YF, so now I do a Fourier transform, a temporal Fourier transform, this is where my signal is sparsest. And another problem we now see, or we don't see, I should say, is in this red box is the non-zero frequency component that you can all clearly see. This is the slightly less black parts than the black parts. That is my signal of interest. So basically we're working at very small signals. So I am very much going to be worried about signal to noise. And it is this bit that's going to encode, that's going to tell me what is happening in terms of time over this artery. Okay, so our first attempt at this was very much a sort of classical, well, I say classical, can one be classical in compressed sensing? A classical compressed sensing approach. So remember, we've got ky, kx, and t, but we get lines for free. So I'm doing Cartesian sampling. Each one of these points is essentially a line in kx, and then I'm sampling in ky and t. This is the design sampling pattern. We're pretty much densely sampling the low frequencies. We then have some sort of variable density across frequency in ky, but it's retrospectively gated, which means that our heart variability is going to introduce some uncertainty, and that gives us this sampling pattern, which we actually feel helps us. So this is good. This is sort of using uncertainty in your measurements to help you. So using this sampling pattern, we can then plug this in, assuming it to be sparse in the YF domain, apply L1 minimization, and that works. So that's one solution. However, what we've subsequently been looking at is saying, well, can we exploit more structure? So often it's very easy to say, yeah, my signal is sparse, but maybe there's a lot more structure to it than that. So here again, I have my data cube. So this is my x, y against time data for a single image. So remember, I've got 2 of these because I've got a phase encode. And if I now take this sort of yellow box and I Fourier transform in time, I get this object, which I think is slightly easier to see that there is some non-zero frequencies happening here. But the key thing is that actually that is my signal model. My signal model has support at the 0 frequencies pretty much across space. I can play about, maybe move to a wavelet domain, but basically pretty much across space. The thing that costs me in terms of samples is trying to sample in time to capture this dynamic component here, which I don't know the location of because I don't know exactly when I do my scan where the carotid artery is going to be. But that is very, very different, and I think this is a key thing to stress. If I were to say my model is sparse in YF, then there would be no difference in terms of my my algorithm wouldn't be able to see the difference between that and something that just had the same support but just randomly distributed. Clearly, we can see that this is much more structured, and so we want to exploit that. So this, to a certain extent, takes us back to what people have already been doing in classical MRI. In classical MRI, so people have known that they've had these sort of cross-shaped type support sets for a while, and if I fully sample, I would reconstruct my cross. If I throw some samples away but not too many, I can still reconstruct my cross because I make sure that my things don't overlap and I get tiling. So this is just classic Fourier sampling at the Nyquist rate. But the big holes in this set imply that I'm being inefficient. I'm basically sampling a lot of stuff that is zero. So the unfold policy says, well, take this, rather than packing it like that, choose a different lattice that packs your crosses in a slightly different way. And we can see that the holes now have shrunk. So we've got for the same recovery, we're sampling faster. What we decided was, well, this is really nice. So we can use this sort of structure, but there's still holes there. And what compressed sensing tells us is that we don't need holes. So we've looked at what we call split support sampling. So let's take this cross, split it into 2 bits, and then things get nice. So I take the static part, and I say, well, if I densely sample, fully sample in KY, I can, if I just saw the static part, I would recover that perfectly. There's no problem. If I just saw the dynamic part, and I subsample, so I fully sample in time, but I subsample in Y on a lattice, again, I can pack this, and I would be able to fully recover. But I don't have one or the other, I have both. It turns out that essentially the number of equations you need to solve this is I just need to do this sampling plus this sampling. So I've got a sort of a 2-lattice sampling structure that allows me to recover it without doing randomness and stuff like that. So the key thing here is I'm exploiting, for this special case, the fact that I have some extra structure. And this has 3 nice advantages. First of all, exhaustive search. I think it's got a terrible name. It gets slagged off so much. Exhaustive search is fine as long as you don't have a combinatorial number of things to search. In this case, we have a linear number of things to search. Where is the dynamic component? And so we can do exhaustive search. It is not a problematic algorithm. We can then do proper, full sparse reconstruction using the pseudo-inverse restricted to the support set. And we can choose our lattice sampling to give us very good condition numbers, typically better at low orders than you would get from a random sampling. And so this is the sort of thing we can achieve now. This is the reference fully sampled carotid data. This is a function of time for each pixel, and this is what we get on a 3.5 times acceleration. So it's maybe difficult to compare those side by side, so let's look at the difference, and we see that really I'm down to just very noisy signals. And I would argue that we've now reached, in this problem, unless we can do something else very fancy, we are noise limited. So it's not so much the sampling that's limiting us, it's the noise. Okay, so I guess the take-home message from that first example is if there's more structure than sparsity, by all means try and use it. I mean, I think that the great thing about compressed sensing is it says, don't think Fourier, don't think sort of standard Nyquist, think degrees of freedom. And then you've got to ask, well, what structure do I have? How complex is my system? Can I, if I have no more structure, then it's approximately sparse, then I should use L1. But if there's more structure, I can maybe do some other clever things. Okay, so my second example is one where this is sort of a mixed result. It's slightly depressing in terms of showing the limitations of what we can do, but we managed to retrieve something out of it. So this is synthetic aperture radar. I'm assuming, given this is a maths audience, that you may not know the details of a synthetic aperture radar, so I brought a toy one along. Here we have my plane. It's a radar, so it's just sending out RF pulses. The RF pulses hit the terrain here, and at this wavefront they'll be reflected back. So at a particular time, I will have the integral of the reflection basically along that wavefront. Let's assume that wavefront's actually a line to make things simple. So I'm sort of making a sort of far field assumption. Then, by the Fourier slice theorem, what I'm doing is sampling in k-space. So this is looking very much like MRI at the moment. So my plane now moves along, and I send out another pulse, and I get the reflection return, and I get another line in k-space. And, oops, it always does that. Right, so I've shown you all the slides now. So, SAR acquisition is very like MRI. I've basically sampled in k-space. I'm sampling over maybe not a complete rectangle, but depending on what assumptions you make, this can be pretty much treated as sampling lines in k-space. And the inaccuracies that assumption can actually be taken care of in the algorithm. So that's not really the issue. Okay, so very much like MRI, we're imaging a scene on the ground. We're using RF signals, but remember that there is a difference. In MRI, I basically excite the molecules in the person being imaged, and they emit radio frequencies which I sense. Here, I am firing a pulse at the ground, and I'm measuring the reflections. So that is a fundamental difference. Quickly, why would we want to do this? So it's an important question because I think that there is a danger in compressed sensing of everyone running and trying to apply compressed sensing to every application possible. You need to have a good reason for wanting to undersample. There must be some pressure in terms of the sampling. And in radar there is. So there are three basic reasons I'm aware of. First of all, unmanned vehicles, if you've got a radar on it, what they want to do now in terms of saving energy, time, cost, is have this radar do as many things as possible. You've got an antenna array. Maybe I want to use it as a comms link. Maybe I want to use it as a tracking radar. Maybe I want to image different places at once. So this is what's called a multifunction radar. So it would be desirable not to have to continually send pulses in one particular direction. Maybe I want to send some pulses in this direction and then some pulses in that direction. But I then have to deal with that when reconstructing. Secondly, radars are getting wider and wider bands to the extent that there are communication systems that are transmitting within that band. So that's going to introduce interference. So I need to notch those out. Worse still, certainly if you want to abide by the law of the land, you're not allowed to transmit in some of these bands. So you have to notch the those frequencies out of the transmitted pulse. So there are going to be holes in your sampling. And so Emmanuel talked briefly about the sort of compression notion. If you've got a radar system where you don't have much computational power, you might want to compress this data in as computationally efficient manner as possible. And I don't think there's much more computationally efficient than just throwing some of the data away. So that would be it's not saying it's the most effective compression scheme, but it's a computationally cheap compression scheme. Okay, so we've got motivation, we've got the system. It looks like MRI, but is it? And this is the crunch. So here I want to compare the wavelet coefficients for an MRI image and a SAR image. I'm hoping you can all tell which is which. This here is, I apologize, it's still not particularly good quality and it's quite a noisy one, but this is a real MRI image of a slice of someone's brain. But you see that the wavelet coefficients down at the low resolution are quite dense, and they get sparser as you go down. So we have something that is approximately sparse. I can approximate this with fewer degrees of freedom. This is a SAR image at different wavelet resolutions, and you can see that there is no change in amplitude across the wavelets. In fact, you can...
How wavelets?
Sorry?
They're both how wavelets?
You've stumped me now. I didn't generate the slides, so it wouldn't matter. It wouldn't matter. So I will explain why this is so bad. In fact, you can throw away most of the low frequency wavelets in this image, and you would get exactly the same SAR image. And this is because SAR imaging is not like optical imaging. You're fundamentally looking at really lousy images, and they are not sparse in wavelets. Okay, so why is it? It's down to the different modality between MRI and radar. Radar is a coherent imaging system. I'm sending a coherent radar pulse, and if within one of my range cells I have lots of reflectors, and they all scatter the RF signal back to me, and let's assume they're all sort of randomly located in terms of their positions within the cell, I'm going to get an incoherent mixing of those reflections. The consequence of that is that the image that I'm reconstructing, the SAR image I'm reconstructing, is essentially an intensity image modulated by Gaussian white noise. So it's multiplicative noise on each pixel. Okay? So think about that. What I'm actually looking at, my image, is Gaussian. It is in no way compressible. So at this point, we all got a bit depressed and thought, well, maybe, I've got this grant, I've got all this money to spend. This is not a particularly good result. Oh dear. But anyway, it turns out that it's not as bad as that. But this again comes down to understanding your signals and your signal models well. SAR images, so this is typically the image that would be...
This Gaussian-like behavior is because of the phase shift between two nearby things that come back, and so...
Absolutely, and you typically have you assume you have within a single sort of pixel cell that multiple things reflecting, and so it's just adding...
There's a time delay such that you get them completely out of phase.
Absolutely, absolutely. And it is, I should say, it's characteristic of most coherent imaging systems. You get this speckle noise. However, and I should say that for things like civilian remote sensing, this is going to be a problem because most of the things you're imaging are absolutely dominated by speckle noise. From a military context, it's not such a problem because there are objects, so man-made objects typically have corners, edges, and these things tend to act as coherent reflectors. So you have something that is reflecting a substantial amount of energy in a coherent manner back at you. And these things have huge intensities. So they're typically 1,000 times larger reflectivity than the background speckle. So these are compressible in the pixel domain. But it fundamentally means we're going to have to deal with that. We've got this is going to cause us lots of noise. We are going to be very challenged by the noise. So our solution is to use a modification of the L1. So we're using what we call a mixed L1, L2 solution. I should say, first of all, this left-hand image, that is a typical SAR image. So that is not, how bad my algorithm is. That is what SAR images look like. They do not, you talk to the radar guys and they're always slightly apologetic that you can't see the objects that you're imaging. They don't look like real objects. So this is from a US database, and I can tell you roughly what we're seeing. This is a road, this is another road here, this is a beacon, so this happens to be a very strong point reflector, and this is a car park. So these are, each one of these things is a car, and that's the quality of the fully sampled data. So we're not looking necessarily to get much better than that, although Emmanuel mentioned those sort of super resolution effects that you can get with L1. Okay, so I'm going to do very mild undersampling. Now I'm going to throw away 50% of my samples, 50% of my pulses, and this is what you get in standard linear back projection, so the linear reconstruction. And what is the problem is, you can't see it on this because we've used a log domain, but the bright targets are really bright. So what happens is once you start undersampling even slightly, they completely dominate. They smear the side lobes associated with them smear over everything, and you just lose everything. So what we've proposed is we can apply compressed sensing to pull out the points, the point reflectors. We can't do anything really about the background speckle. The best we could do at the moment, as far as we know, is some form of sort of L2 inversion. So what we're going to do is we apply a lasso type program where we choose our lambda not so it's very small, but so that it discriminates between coherent reflectors and background speckle, and we basically pull out. It's not so clear on this slide, but if you look at these images, you can see it's pulling out most of the sharp point-like targets in the original image. Then we apply a data consistency term which just says take the residual, L2 invert it, and add it to the stuff that you've pulled out with the sparse component, and you actually, again, you can't see it here unfortunately, but you can get some of the background image still preserved. You've clearly lost resolution because we're not doing anything clever here, but you've removed the fact that you've got these sort of side lobes completely spilling out over everything. So it does provide an improved performance, but it's not great, and it's a low undersampling rate. So maybe we're maybe this isn't such a good application. Well, again, if we're talking militarily, one thing they want to do with these SAR images is not so much just look at them, but actually detect and classify typically tanks, aircraft, things like that. So here we've got a SAR image with a tank. Again, typical of SAR images, you can't tell that it's really a tank, but unless you're very experienced with these things. Now I'm going to show you that actually we can, if we have a specific task of detection or classification, we can push this much harder than one might do in terms of producing just an image. So I have 25% Nyquist. This is my back projection. It's terrible. This is my compressed sensing. It's very difficult to see. Let me blow up the tanks. Sorry, no pun intended. This is my tank in my compressed sensing, and there is something here is the tank. But doing detection and classification on the back projection is not so good. Doing it on the compressed sensing data is much better. And if we look at, so I don't want to go in detail with these, but basically at 25% data, with compressed sensing, reconstruction, randomly throwing away lines, I can get pretty much the same classification performance as I would get if I had the full data, whereas I've suffered quite substantially with back projection. Okay, so I guess the take-home message for the SAR compressed sensing is compressed sensing doesn't always work as well as you might want, depending on your signal model, but there may be something you can recover if you target application-specific goals. So here we were looking at detection and classification, and it does perform quite well. It allows you to do a degree of undersampling. So the final application I want to look at is one where we're truly challenged in terms of RF, which is wideband spectral sensing. And I'm sure Emmanuel will be saying more on this later in the week. Again, this is a beautiful sort of natural example of where we might want to do compressed sensing. So again, let me try and motivate it from what do we want to do engineering-wise? I'm interested in looking over a wide spectral band, maybe a few gigahertz, maybe tens of gigahertz. And if this is a military application, this may be because I'm interested in looking for what radars are present or what comms systems in a battlefield scenario, or in a wireless comms scenario, there's cooperative comms where you may want to look for holes in the spectrum where you can transmit. So this is what's called cognitive radio. So there's this. So the question we ask is, can we monitor this full, huge band simultaneously, all frequencies at once, but in a practical manner? Now, you could build, and you can build, people have built sampling systems that sample up at gigahertz. You look at optical communication systems, they have devices that do sample at these rates. But they are incredibly expensive, consume vast quantities of power, are not practical in a number of the applications we're interested in. So we want to be able to do this in an efficient manner, and obviously compressed sensing, if I could throw away some of these samples, sample much less, then that would be brilliant. And the work that I'm going to talk about initially and then build upon actually predates compressed sensing by 10 years. It's Feng and Bresler, 1996, and it's what's called multi-coset sampling. So here I have my waveform that I want to sample, and what I'm going to do is I'm going to sample it periodically at periods TS, and within that period I'm going to take a number of samples. So I'm going to take Q different samples within a window. Let's think of that window in terms of Nyquist periods. So it's going to have, that window is going to have L Nyquist periods, and I'm going to take Q samples within it. So my average sampling rate is going to be Q times my bandwidth divided by L. And as long as Q is less than L, I'm subsampling. And one can realize this in a multi-channel structure. So you have your signal coming in here, and you have a delay, and then a sampler. You have another delay here, and a sampler, etc. So there's very practical structures that can be built to do this. And the nice thing about this is, again, it's one of these systems that sits somewhere between classical Fourier and complete sort of random sampling, and so admits a beautiful analysis. So each one of these points in this, if I view it as a multi-channel system, this point will be sampled. I'll be sampling here, and then I'll be sampling again every L Nyquist periods, and so I'm sampling that at 1 over L Nyquist. So I'm getting lots of aliasing. I'm then sampling this one again at 1 over L sampling. So each one of these channels can be just viewed as classical sampling, where I'm undersampling. So we know what happens when you undersample. You fold over the spectrum. So if I do the discrete time Fourier transform of one of these sampling outputs, I'm getting my it consists of the sum of all the spectral slices that are aliased of my original signal. So I've basically folded all these things over. The purpose of the delay is the delay introduces a phase shift, which is up here. Now if I rearrange this slightly, so I'm going to pull this the phase shift that's a function of omega down onto the left-hand side, I now have a modified discrete Fourier transform representation of the output, which I'm going to call Zi of omega. I have a linear sum here that is essentially a partial Fourier transform with frequencies associated with the delays, and then I have the spectral slices of X. So I have a linear system, I have a set of observations, and I have a set of inputs, and if I assume that I have only occupying a small number of the spectral bands, then this guy here is going to be sparse. Okay? The problem with this equation as it is that this matrix isn't a function of omega. That's good. These guys are a function of omega. That's bad. So I'm still really in a function space sort of representation. So as an engineer, I like to draw pictures. So this is what we actually have. We don't have a finite dimensional vector here. We have a vector of spectral slices going through a Fourier submatrix, giving me my observed spectral slices. So if I'm going to do some form of compressed sensing on this, I need to reduce it down to a finite dimensional space. Well, what's the easiest way to do this is just to integrate over those spectral slices. And this is what was proposed way back in '96 by Ping Feng. So I can actually build what is essentially a covariance matrix of my observed data. And because of this structure, the covariance matrix of my observed data is just the covariance matrix, so this integrated covariance matrix over frequency of my input signal that comes in here, times pre and post multiplied by phi and phi Hermitian transpose. And although we've written this down in the frequency domain, the observed covariance matrix can be got. It's basically just a cross-correlation matrix. We can get it from the observed samples through the introduction of what are called fractional delay filters. But anyone who does DSP knows we can do that. That's not a problem. So I can basically observe RZ, and I know that RZ is phi RS phi Hermitian transposed, and RS is a covariance matrix associated with sparse spectral slices. So RS is joint sparse, joint K-sparse. So one approach to solving this, and this is what was, so Michali and Elder sort of re-stumbled upon this in 2009 and sort of reinvented this form of sampling from a compressed sensing perspective. And so from a compressed sensing perspective, I could take this, I can take say a Cholesky decomposition of RZ, and then I have a linear system. It's got joint sparsity, but I can throw standard L1 minimization or combinatorial optimization, greedy methods, what have you, and I can retrieve this. So this gives me a recovery system where if I allow myself, impractically, I allow myself combinatorial optimization, as long as I'm sampling at twice the Landau rate. The Landau rate is the fundamental lowest rate that I could sample at if I knew where the spectral support was. So if I sample at twice that, then I can actually recover this. Of course, if I'm using things like L1 minimization or compressed sensing tools, I have this log factor penalty. So there'll be a log factor penalty that I will have to pay to incur in this case. So what's really interesting, and it's always good, I really liked Emmanuel's talk where you look back over what people have done, because it is so important to see what's been done before. So if we look back at what Feng and Bresler did in '96, okay, they didn't. This is the most general case. They assumed something that was slightly easier, but actually in practice almost always met, and that is they said, well, let's suppose these bands are incoherent, by which I mean that this is a covariance matrix that's K sparse and will typically have rank K. If it has rank less than K, that's telling me that some of the signals in different bands are fully correlated, which is unusual. So when this has full rank, this problem has already been solved in the array signal processing community. We can solve it using what's called the music algorithm, which for mathematicians is just an eigenvalue decomposition, and it's essentially saying that I have observed enough different dimensions to actually be able to see the full signal subspace. So, I mean, again, you can actually view the music algorithm as an exhaustive search. But it's an exhaustive search that's linear rather than combinatorial. And now we're right down at the Landau rate, so we can achieve the Landau rate. So let me give you an example of what this looks like. What we're doing, we take our observed covariance matrix, we form an orthonormal basis of the signal subspace, so basically through an eigenvalue decomposition. The classic, and there's different ways you can do this, but in music, the classic thing to do is then project your columns of phi into what's called the noise subspace, so the orthogonal complement to the signal subspace. And obviously, if your phi is one of the occupied spectral slices, it should belong to the signal subspace. So it should be orthogonal to the noise subspace. And lo and behold, we plot this, and you get zeros at all the occupied bands. So we can do this. Again, we're massively exploiting structure. We have to be careful. We're sampling lots in time, and the structure has a very specific joint sparse structure that allows us to do this. You can't apply music in general to general compressed sensing problems. But this means that we're avoiding iterative reconstruction techniques, and we've lost the log penalty, at least in the noiseless case. What compressed sensing tells us, which is quite nice, is compressed sensing says, well, actually, what we do know is that if I choose these delays at random, so I randomly position them, then with high probability I'm going to have a near optimal conditioning on my reconstruction matrix for phi, irrespective of where my support is. So compressed sensing is it's sort of closed the loop on this and explained, how well we can expect this to perform in terms of robustness to noise. So let me now look quickly at robustness to noise. I should say there's different types of noise. In this scenario, I might have noise here, which in this scenario would consist of quantization noise. I might have noise here, which would in this scanning scenario would consist of antenna noise that I get across all frequencies. So they're not that different. This one comes through the operator phi, this one doesn't. From a physical point of view, the operator phi in pretty much any sensing system is going to have a operator norm of less than or equal to 1. If I allow this thing to have a higher operator norm, I'm kind of cheating because I'm saying I can get rid of this noise just by amplifying my signal before I add my quantization noise, which is, as engineers know, sadly doesn't work. But this noise always comes through here anyway. So what we know I don't want to spoil Emmanuel's talk tomorrow, so there's this thing called the restricted isometry property, which is a property of random matrices. If we have that I bound my my operator norm of phi to be less than 1, then typically with the restricted isometry property, this guy is going to be, so the submatrix is going to have an operator norm that scales as the square root of the subsampling. And you then plug that in and you get that you're going to get a 3 dB, typically a 3 dB drop in SNR performance as you undersample. So this is the theory, this is my 3 dB line. These are some simulations that my postdoc Michael Lexer has done on, this is the solid lines are the ones to look at, these are the multi-coset sampling, the dashed lines are a different system. And you can see that we do truly see a 3 dB drop per decade, per octave, sorry. So this may not be a problem, but what you're throwing away with undersampling is you are throwing away a certain amount of processing gain that you can get from oversampling. And so we showed this to one radar guy who was particularly interested in detection and tracking radars. So they want to detect very small signals within the noise, and for them SNR is everything. And so you show them this and they go, I am not interested. So again, it's very much a question of what is the specific goals and that are going to define the limiting factor. This may prove to be the limiting factor in many applications. Okay, so I want to, I've got 3 minutes, I'll see if I can do this. Finally end by a piece of work we've recently done, which again, I think it comes down to asking the question, what do I want from my reconstructed signal? Do I want to reconstruct the signal at all? So in cognitive radio, for example, there are a number of papers coming out in compressed sensing for cognitive radio. Cognitive radio, you're interested in looking over the spectral frequencies and saying, where are there gaps in the frequency spectrum that I can exploit? So actually what you want to do is just estimate the power spectral density. This is not a reconstruction problem. This is an estimation problem. It turns out that if we assume that our signal is wide-sense stationary, okay, that may be a very strong assumption, but let's make that assumption for now. Then the covariance matrix of the signal, RS, is actually diagonal. So this is a k-sparse, if it's got sparse support, it's k-sparse, but it's diagonal. So this is much, much easier. And furthermore, the actual diagonal elements of RS act as a finite resolution power spectral density estimate. So I now have the same number of equations, but I have fewer unknowns, much fewer unknowns. The square root of, in this case, the square root of L unknowns. So I can basically convert my covariance matrix into a vector. I must be careful to throw away the repeated measurements due to the Hermitian symmetry and the diagonal. But the individual elements of my covariance matrix can be written in terms of a sum now just of the diagonal elements of RS, which again, strangely, gives us a partial Fourier observation matrix. So this time, previously we had a partial Fourier observation matrix which had just a single delay up in this term now. Now we have the difference between the delays. Okay, so first of all, I don't actually need compressed sensing at all. If I choose my Q, remember this is the number of samples per repetition period, to be large enough, then, well, first of all, the rank of psi is going to be defined by Q. It's roughly going to go as Q squared over 2. And I can usually achieve that by, say, randomly choosing my sampling pattern. So I now have this matrix that is V equals psi, sorry, U equals psi V, or V equals psi dagger U. And as long as I have full rank, I can invert this. And I will have the full rank if this condition is typically held. No sparsity involved at all. So I'm basically saying this is a case where compressed sensing has not helped me at all. I can do pseudo-inverse on this, and because, remember, my undersampling ratio is roughly Q over L, but because I've got a Q squared on this side, if I choose Q and L and let them go to infinity at an appropriate rate, I can still let my sampling rate go arbitrarily low, and I can still recover my power spectral density. Now this turns out not to be an unknown problem. It's known since probably even before the 70s that with random sampling techniques you can estimate the power spectral density. The key thing is we're estimating a statistic of the signal, not trying to reconstruct it. So reconstruction sampling theorems do not apply here. Okay, so that, not wanting to end on a negative note, let me quickly put in a positive thing. What happens if I know I've also got sparsity? Does that help me? And the answer is yes, I can do even better, because obviously this equation here is just a linear equation I want to invert, and if I'm in a scenario where where Q is too small with respect to L, this is going to be underdetermined. So if I'm really undersampling, and then I might want to introduce compressed sensing. And here's a really beautiful thing about this particular mathematical system. So I might say, let's try and solve the L1 minimization. Sounds a good thing to do. However, if I look carefully, the diagonal elements of my covariance matrix Rz are just this partial Fourier expansion times my diagonal elements of Rs. But this guy is just a constant because this is associated with the difference in delays. So I'm actually measuring directly my L1 norm. So I have this problem where I want to minimize my L1 norm. Oh no, I don't need to do that. I've got it. I also have another thing, which is that the V's are non-negative because it's a power spectral density estimate. So I can actually replace the L1 minimization with a non-negatively squared solution, and this is just acting as a proxy for my L1. It's doing exactly the same thing. And I was very interested to find out that in the radio astronomy literature, where again they did compressed sensing type ideas way back in the 70s, but without the theory, they also found out that using non-negative least squares works really well. But as far as I know, they didn't follow it up with any theory. So here, the theory explains why non-negative least squares works for them. It's basically a proxy for L1. Okay, so quickly some examples. This is a white noise signal with some notches. I'm sampling at a third of the Landau, but you shouldn't be impressed by that because the Landau rate means nothing because we're not trying to reconstruct. But my pseudo-inverse will obviously give me my reconstructed signal, and so will my non-negative least squares because they're exactly the same in this case. If I push it a bit harder, my pseudo-inverse falls down, so this is just classic compressed sensing beating back projection, but now my compressed sensing is being done not by L1 minimization, but by non-negative least squares. So, final thoughts as I've gone slightly over. Compressed sensing provides us with this fantastic new framework with which we can undersample, we can exploit sparse representations, and so traditional sampling theory we should put to one side. In practice, I think there are things that you must bear in mind when doing this and may well prove to be the defining factors of how well you can do. What are your sampling constraints? What is your signal model? What are the S&R constraints from an engineering perspective? And what are your application goals? And finally, an unashamed plug for if you're interested in this subject, which clearly you are because you've come here, you should all come up to Edinburgh at the end of June. We've got a SPARS 11, which is signal processing and adaptive sparse structured representations. It's the third in the series. We've got a fantastic lineup of plenary speakers. I'll end there.
Okay, other questions? Yes, please.
Yeah, I don't have any question, just a comment.
Yeah.
So you mentioned the Munich algorithm by Fung and Bressner. Very recently, I think last year, Bressner and his student Lee has proposed another algorithm, put it on archive.
Iterative music, yeah.
I'm Munich. Yeah, exactly. Yeah. So I just wondering whether it can help your research.
Yeah, so at exactly the same time, so Lee and Bresler put up iterative music. Myself with Yanina Elder put up something which we called Rank Aware Pursuit, and there's a third one, Kim et al. From Korea have put up something that is again. So yeah, it was but yeah, there is people are looking at the link between doing things like L1 and greedy algorithms in the single sparse case, up to music in the full rank case, and you know how do you best interpolate that?
In our example, is it possible to organize the RF pulses to do something like background subtraction? Like suppose I want to kind of really collect information about what we could think about there's a difference about two consecutive frames. I don't want to re-image the same thing.
So this was my first thought, thinking this is fantastic. We just want to do a difference of images.
Is there a way to do
you can
the RF pulses to do
the
this?
problem is that you can in theory do it, but you don't have exact control of timing because it's retrospectively gated. Secondly, there are even when you're not introducing velocity encoding on the phase, you do get phase differences. So to actually get it to try and subtract, we failed, and we looked at that and said, surely we can pull this down and make it a really, really sparse object.
But what I was thinking more is in the physical device itself. That is, I would manufacture new RF pulses,
Right.
and I would try to make this pulse measure.
Just I see what you're saying.
Try to do it as a post-processing.
Yeah. No, I see what you're saying.
To kind of
We haven't looked at it. It's an interesting idea. Yes. Yeah.
Well, if there are no other questions, thank you again.